Hello, calculus students. Today we're going to take a look at our calendar first to set uh, a path for the week. I'm in remote chapter 7 section in the calendar page. As you can see, for today, the 23rd, we're going to be doing our OneNote check-in, which really just entails us literally looking at what we're supposed to be doing here on OneNote. There is a collaboration space video page that I've created or section that I've created, and you'll take a look at that anytime you want to ask me questions pertaining to the video. We're going to take a look at section 7.2 notes today, so we are moving forward, and we're going to take a look and see what we can do with that. Today will be primarily a note-taking day. Well, tomorrow you can see we'll be continuing with our respective homework problems that we typically do. So let's jump in, section 7.2. Now, if you recall, the last thing we were doing was example 4 in this particular section. We had finished example 4 and hadn't yet begun example 5. I wanted to touch base with you, though, regarding, just as you can see here, this little icon at the top. This is a blank version of the notes. So if you want a blank version, some of you down the road um, will like using this, although you already have the notes from section 7.2. But if you double click on it, just to kind of give you perspective, it should, on your computer, might take me a little bit here. There it is. It should open it up and you guys can print that off at home. I would enable editing and then go ahead and print it off so you have a blank version. So when we do section 7.3, for example, this will be important for you probably or possibly. So that's available to you. But like I was saying, we had begun the notes and gotten through all the way to, take a look here, example 4. And there you go. So example 4, if you guys recall, did entail us finding the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So we're taking this two-dimensional object with a very specific area, and we're revolving it about the y-axis. So we're actually creating what you see below here, which is a kind of three-dimensional depiction of this, of which has a volume v sub 1 and a volume v sub 2. And I broke it up into two different integrals because up above what we're looking at technically are two different bounded areas, one of which has a delta y that we took a look at, if you recall, via our analysis in this little piecewise function we set up, and also this little area below with a different delta y. I do have a v sub 1 and a v sub 2. The v sub 1 is more complicated because you're subtracting out this little circular region that, as you get closer and closer to this ordered pair 0, 1, ends up being, well, it ends up being a smaller circle to the point where it's literally a point. So this subtraction has to be done. So v sub 1 is this, like I said, this volume that we're calculating, and we did calculate, while v sub 2 is this cylindrical region. Now, what I didn't finish with, yes, we did come up with the answer of 3 pi over 2, but what I didn't finish with was kind of filling in the gaps of the actual math that led to 3 pi over 2. So let me go ahead and do that. It shouldn't take us but a little bit here to do the analysis. So if I do the math with the first integral, I'll have, let's see, I'll have pi times, and if in fact we were to take the integral of this, it lends itself to 2y minus y squared over 2, and we're doing this from 1 to 2, if you recall. Those are the lower and upper bound values. And I'm going to add that then to the following, pi times y, because the integral of just 1, v sub 2, that integrand ends up being 1. So that, of course, then ends up being, well, just y. And that will be done from 0 to 1. The math then ends up being fairly nice. And yes, you can plug in 2. You can plug in 1, subtract those two, and that ends up being simply pi over 2. Okay. And then the second ends up being, if you just plugged in 1, you get 1, plug in 0, subtract the 2, that's just pi. So you're adding those. So pi over 2 plus pi. Of course, that ends up to be 3 pi over 2. Note that the first integral is actually the second integral because I kind of flip-flopped. Let's just say that the v sub 2 integral is pi times the integral from 0 to 1 of 1 dy. And that represents the volume of a right circular cylinder of radius 1 and height 1. This portion of the volume could have been determined without using calculus. In other words, we could have found v sub 2 just by conventional means of capital B times h, which, as you know, for a cylinder, at least you should know from geometry, if you remember, the volume of a cylinder is pi r squared times h. So we didn't technically have to use calculus for that second volume, v sub 2. All right, let's move on. Example 5. So this particular problem is going to require a little bit more analysis, wherein we will kind of break down using a little bit of a different equation. I'll explain. Manufacturing. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches, as shown in the figure 7.23a. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Okay, so we've got a nice depiction, kind of three-dimensionally, what's happening. It shouldn't come as a big surprise taking a look at a circle and its respective cross-section, or sphere, I guess, if you want to think of it from that perspective. But the cross-section of the sphere is, in fact, a circle. The equation that particularly speaks to what we're doing here in context, and if you look at kind of the aspects of, well, if the radius is 5, simply then the r squared would be, well, 5 squared, which is 25. Okay, so that then lends itself to an equation that where if you wanted to get y by itself, this is just a quick and nice way to see what this would look like as an equation in terms of x, or y written in terms of x, which would look something like this. So y equals square root 25 minus x squared. Okay. So in the context of what we see off to the right, I do want to highlight that we do know our radius. Call it capital R. Okay. And of course, that's 5 inches. And then eventually, as you kind of look down, using that solid of revolution, but kind of going backwards, so to speak, using a three-dimensional now to a two-dimensional depiction, we've got the equation that we just deciphered. The R equation, or equation for R, is the square root of 25 minus x squared. Okay. Well, let's put this together into equation format of volume. So volume is equal to, as we remember, pi times the integral from A to B, and then we'll do, generically speaking, we'll do the capital R function, quantity squared, minus, and we haven't talked about it yet, but lowercase r, quantity squared. We've talked about it in prior examples, but we haven't yet talked about it on this problem. So that would be kind of the general depiction of what's happening here. We're going to talk about lowercase r in a quick moment here. We're going to take a look, start plugging things in. Let's actually also, as we kind of forecast what that'll entail, look at the second picture, because the second picture is really where we're going to be able to easily see the connections being made to the integration. So lowercase r, which actually, why don't we just look at it in the context of the picture, that right there speaks to the distance literally between y equals 3. So you're carving out a hole out of this sphere. You're carving out a hole. The distance, though, between the horizontal line y equals 3 and the center of the circle. So when you revolve this two-dimensional object about the horizontal line y equals 0 and the line y equals 3 is taken into account, where you're subtracting it off, you're going to revolve it such that you're creating this sphere with a hole in it. interestingly enough, it does relate nicely to all washer problems, but obviously there's a little bit more involved with the notation. All right, so we're going to find the integral from -4 to 4. And if you're wondering why that is, if you take a look at, in the context of our picture again, this ordered pair is -4, 3. I know that because that particular ordered pair has to have a y of 3. And if you were to plug in 3 into the equation, the square root of 25 minus x squared, if you plug in 3 technically for y, you'll get x to be -4. There's two different versions of this, so to speak, because as you recall, there's a plus and a minus when you square root. So plus or minus, technically, 4 is what we're looking at for x. Again, plugging in 3 for y. So we're going from -4 to 4 on the two-dimensional depiction. All right, so then we plug in our function. So our function, again, if you recall, was the square root of 25 minus x squared, and that quantity is squared. Okay, I'll leave the bracket off for the moment. Minus, and we're going to subtract out the whole. And that particular value, of course, or function as a value in this case is simply just 3. As we said, y equals 3. Okay, we're going to be squaring that as well. All right, so now we're going to continue. Now that everything is set up and ready to go, the hard part is over. So let's go ahead and do the analysis of simplifying and then integrating. So the integral from -4 to 4, the quantity, the square root of 25 minus x squared is just 25 minus x squared, which is quite nice. Then, of course, minus what, 3 squared, which is 9. And don't forget, of course, still dx. And that then lends itself to the following. So equals pi times the integral -4 to 4 of 16 minus x squared dx. And then we continue with the following. Pi times we integrate such that this is just simply 16x. And this right here is simply just -x cubed over 3. And we're doing, again, -4 to 4 as our bounds, working with those. And then we can finish this thing where if we were to plug in 4, subtract, and -4, subtract, I will be more lenient, as you guys recall from before we were remote learning here, that I would allow you guys to use your calculator pretty much after this point on most problems. Now, this particular problem took us quite a bit of time, but I do want to highlight what solids with known cross-sections entail as we finish things up for today. And that will pretty much be it. I won't do any more examples, but let's take a look. So solids with known cross-sections. So with the disk method, you can find the volume of a solid having a circular cross-section with area of A equals pi r squared. This method can be generalized to solids of any shape, as long as you know a formula for the area of an arbitrary cross-section. Some common cross-sections are squares, rectangles, triangles, semicircles, and trapezoids. So here are some volumes of solids with known cross-sections, the first of which is taken, an area, A of x, taken perpendicular to the x-axis. And then we'll talk about, of course, also A of y, though perpendicular to the y-axis. So the integrals are a bit different in that one is with respect to x from A to B. And then look at the picture below. Figure 7.24 is pretty nice and how it kind of relates that information. Notice delta x, because of the perpendicularity to the x-axis, is what we're assessing. We're going to find that cross-section perpendicular to the x-axis, and the integral speaks to that. And then the second picture that you see is A of y, and because now we're talking about perpendicular to the y-axis, notice that the x and y-axis is kind of laid on its side here as opposed to kind of running vertically and horizontally. Anyways, the delta y, as you see, is now perpendicular, and of course, look at the equation for volume there. So that concludes today's notes, and we'll continue, of course, tomorrow.